Hi, my name is Emma Skelton. I'm a PhD candidate in Earth and Climate Sciences, working with Carl Coitz and Seth Campbell. And for the Bourne Symposium this year, I'll be sharing some of my work using phase-sensitive radar measurements that have revealed a rheologically distinct layer at the Denali ice core site. So the Denali ice core was recovered in 2013 from the Central Alaska Range in Denali National Park, Alaska. Instead of being drilled on Denali proper, it was recovered from kind of the neighboring peak called Mount Hunter or Baguya. In 2022, a group of UMaine grad students and I went back to the site of the Denali Ice Core, which is the summit plateau of Baguya, to collect some radar measurements using some newer technologies. And one of those radar measurements is autonomous phase-sensitive radar, which uses repeated static measurements over a period of time to capture the vertical velocity of the ice. We took a series of these measurements across the summit plateau. So these are spaced about 50 meters apart. And in total, we took a total of about 22 measurements. The center of these two kind of transects where we collected measurements is where the Denali ice core was recovered from. And in addition to these static measurements, using the phase-sensitive radar that allow us to determine the vertical velocity of the ice pack, we also took a series of what are called polarimetric measurements with the same radar system. And so these measurements involve rotating the antennas in different orientations to capitalize on the difference in the electromagnetic propagation speeds between different polarizations of the wave to infer information about ice fabric. And so there's two different sets of measurements that we take in this polarimetric measurement suite where the antennas are cold polarized or cross polarized. And again, those measurements allow us to infer information about ice fabric or structure, whereas the repeated measurements allow us to infer information about the vertical velocity or deformation rates of the ice. To orient us to what the Denali ice core looks like beneath the subsurface, we have a figure from a radargram that's just using a standard impulse GPR. And so this is a transect going over the Denali ice core site, where the Denali ice core is represented by this blue line here. The key features to point out here is that there's a substantial amount of fern in the top 50 to 100 meters of the ice at this site. In total, the depth is about 200 meters. And we have a very clear bedrock reflection, and we see that the bedrock is not flat, it's undulating, and the Denali ice core was recovered kind of from the deepest section of this trough between kind of these higher points in bedrock below the ice. So we took phase-sensitive measurements right at the Denali ice core site, and I'll show you what that kind of looks like first. So we took two different measurements, one on June 10th and then one 2 weeks later. The first thing that we do is we look at the power return of those measurements to make sure that we line up, which is shown by the figure here. The key feature to look at from this first plot of power versus depth is that we see a substantial increase in power that aligns with where the bedrock reflection is. Then we look at the phase difference between these two measurements, and we analyze the coherence between those measurements as well. And so we're only going to use measurements between the first and initial measurement that have a coherence or a correlation between them of greater than 90% to make sure that we're imaging the same layer of ice before we calculate the inglacial movement. The phase is then converted to range, and then we use the difference in range or depth over time to calculate vertical velocity. And so this blue profile here shows us a relative vertical velocity between different layers within the ice pack, which then we're able to anchor at the bedrock because we know that ice is frozen at the base from the drilling season and very cold temperature measurements taken from the borehole. And so this allows us to have a corrected or more absolute vertical velocity profile, showing the deformation rates of the ice decreasing with depth. And then our final kind of processing step for these data is to apply a density correction. This accounts for the difference in radar wave propagation speed between fern and ice and allows us to a bit more accurately depict the full depth scale of the ice pack here, which we know is a little bit over 200 meters depth from actually drilling ice at the site. So the key feature that you may have noticed from looking at these vertical velocity profiles is this section here. There's this little kink in the profile where we see this pocket of ice that has a more negative vertical velocity than the ice above or below it. And so that indicates that there's a section of ice that is compressing at a faster rate than the ice position directly above or below it. And so I'll more colloquially refer to this as the squishy ice that we're observing in the PRES measurements at the Denali Ice Core site. As I mentioned earlier, we didn't just take one series of measurements at the ice core site, but we took a whole series of measurements across the summit plateau. And we see the same feature of this squishy pocket in the vertical velocity profile at nearly all of the sites that we measured. The depth of this squishy pocket varies, but it varies relative to the bedrock depth. So keeping in mind that radargram figure that we looked at earlier, showing that the bedrock is not flat, but it's actually undulating. This helps support the idea that there is this kind of squishy ice at not just one measurement site, but all of it, which helps support the idea that there is a rheologically distinct layer of ice rather than just something odd going on directly at the core site. Our other radar measurements that we used polarimetry to look at further support this idea of this rheologically distinct layer. The polarimetric measurements reveal a disruption in the birefringence of the ice at depths that align with where we observe this squishy pocket in the vertical PRES, in the PRES profile of the vertical velocity. What could cause the squishy ice that we observe in these radar measurements? So there's a few different options. One is that it's a radar artifact, so something else is being reflected that is introducing this inflection point in our radar data that's causing us to view this as a squishy pocket. The second option is that there is a change in the ice composition that's causing it to behave differently. And the third option would be that there was some sort of climatic shift that causes a change in the ice properties or snow properties upon deposition that is preserved as the ice has been buried with depth. And this kind of hypothesis aligns with different radar measurements that have been observed in places like Antarctica, where we see a shift in the vertical velocity profile that align roughly with major climatic transitions between glacial and interglacial periods. First, we look for radar artifacts and if there's a potential for anything else in the environment that could be introducing this change in the profile that we see. And so one potential source of a radar artifact could be if there was a buried crevasse. And so there are buried crevasses at the site. It is a very complicated site. There's lots of interesting ice dynamics at play. We mapped out where we observed buried crevasses from GPR data taken at the site in 2022 and using information from the site in 2013. And we observed that there is radar evidence of a significant buried crevasse that crosses the summit plateau at depth. However, the depth and propagation angle of this buried crevasse is inconsistent with the squishy ice signature that we observe in the phase-sensitive radar measurements. And so because of this, we note that there are complicated ice dynamics at play. However, there is nothing that we see that can fully support that what we are interpreting as squishy ice is actually a radar artifact. And so we kind of cross the potential for radar artifacts off the list here. To investigate if there is a change in ice composition that's causing this rheologically distinct layer of ice, I went out to the National Ice Core facility in the fall to take measurements of the archived Denali ice. One series of measurements that I took was using the electrical conductivity measurements. And this is really under the wheelhouse of a good friend, Liam Kirkpatrick at the University of Washington, who trained me on the system and allowed me to use it on a section of the Denali Ice Core. We took two different series of measurements, one with alternating current, one with direct current, and both of these measurements showed really nice layering within the core itself. Results from these electrical conductivity measurements are shown here. I only sampled or measured about 30 meters of the archived Denali ice core. One thing to note is the exact depth at which we observe the squishy ice in the phase-sensitive radar profile is subject to about a 10% error, and that is just inherent to these system of radar measurements. And so we have a bit of a range of the Denali ice core where this squishy ice pocket could be. And so that's why I took about 30 meters of measurements to try to see if there's any sort of significant signal change that we could tie to a potential place where the squishy ice may be buried within the ice. And the key thing that we observed from the electrical conductivity measurements in terms of a significant signal change is that at a little bit below 160 meters depth, in the DC current, there's a substantial shift from very high conductivity to very low conductivity. And so that could support the hypothesis that there is some sort of composition change in terms of dustiness of the ice that is causing it to behave somewhat differently in this kind of narrow window. The second series of measurements that I took was hyperspectral imagery. And this is under the wheelhouse of Andrei Kurbatov and Rasheen Rumsey at UMaine. And again, they trained me on the system and then allowed me to use it to scan this 30-meter section of Denali ice. Preliminary data from these HSI measurements really mostly show that there is increased fracturing in the area where we believe the squishy ice to be. And that, I think, is most evident just by photos of the core itself. The picture on the left here shows really nice, intact, visible layering. And this is ice in the Denali ice core that sits above where we suspect the squishy pocket would be. Whereas the figure on the right shows much more heavily fractured ice, which is in this range where we believe the squishy ice to be. And so these just visible observations of the ice itself from nice, layered, intact to very fractured ice was visibly striking to me when I was looking at the ice itself, and that was quite interesting. And there's different reasons that could cause this fracturing of ice that could happen during the drilling process. But the fact that this ice that we believe to be rheologically different is much more fractured than the ice above it further supports our notion that there is something real happening that's different in the ice itself that we're observing with these phase-sensitive radar measurements. Finally, we look into the question of whether or not there was a substantial climatic shift that could be causing this kind of change in ice properties that's observed. And to do this, we looked at the age of the ice in the area where we believe the squishy pocket to be, and we used the annual layer counting age scale provided by Dom Winsky to look at this. And so again, using or keeping in mind our uncertainty of about 10% in depth, it's hard to tie down precisely to a year when this squishy ice was deposited, but we know it's less than 1,000 years old. And so that rules out any sort of major glacial interglacial transition that could have happened. And it implies that there could be a much more recent climatic change that we are observing by the different behavior of this ice. So to look at this, we looked at the stable isotope record from the ice core itself, which is work done by Carl and Dom. And the kind of key takeaway from the geochemistry data here is shown in the deuterium excess record, where we see a substantial shift in the deuterium excess between the medieval climate anomaly and the Little Ice Age. And this transition occurs at the approximate age of where we think the squishy ice aligns in the Denali ice core. And so all of that leads us to believe that there is a phase-sensitive radar really does reveal rheologically distinct layer of ice at the Denali ice core site, and that this is potentially due to a hydroclimate shift that's aligned with the onset of the Little Ice Age. A lot of different folks have contributed to this work over the last year or so, including help with radar interpretation, those who helped collect the data in the field, those who have worked on the geochemistry of the Denali ice core itself, and those who helped me with direct measurements of the core at the National Science Foundation ice core facility this fall. And funding for this work, both in terms of radar measurements and core measurements, have come from a variety of sources. Thank you so much.